have two sessions in the symposium, so apologize for that. Just a few reminders. We do have a Slack channel that you can join. And there's a Slack page, and there's a Neutrino channel. So each session has a channel that you can write messages there. And the talks of the day are already available in the site of the symposium. There's a sign-up sheet just for us to keep track of who is actually attending these sessions. And also, I'd like to remind you that all the white papers that are the subject of this symposium are available at the lastfree.org page, which is linked from the starting page of this symposium. So without further ado, we have a very busy session today. Starting with, I'm going to chair the session of neutrinos. And the conveners of the neutrino sessions are Harold Yepes from Yachay Tech in Ecuador, Jorge Molina from Universidad Nacional de Asunción in Paraguay, and Alfredo Aranda from University of Colima, and also Tepatitlán's Institute of Theoretical Studies in Mexico. And I think Harold is going to conduct the slides, and I'm going to keep track of time. So we have half an hour for the plenary talk, which is going to discuss the white papers that were submitted, and then 10 minutes for each of the 8 papers that were submitted for the neutrino session. So Harold, please, I'll tell you when you have 5 minutes left, okay?
Okay, thank you. Let's see if you are able to see my slides. Do you? Yeah?
Yes.
Okay.
Yes.
Okay. Thank you very much, Rogerio. So I'm going to start now, right?
Okay, yeah, just start.
Okay, thank you very much for this opportunity to really represent the Neutrino Physics Working Group on LAFRI. I pretend that this talk will be more focused on the contributions, as you already say, about the white papers were submitted to the strict and rigorous presentation on theory and experimental side. Okay, so if we move to the next slide, so that's the outline I'm going to follow. Okay, I'm going to use the pointer because I really have the right to do it. Okay, but basically it's the outline of this report. Okay, so just starting going by the number of white papers for neutrino physics per country, I would like to share with you that the list, or what finally sent 5 countries. We have five countries sending white papers. Okay, Argentina, Colombia, Ecuador, Brazil, and Peru. Okay, in total we had 15 papers for checking. Okay, very nice, very didactic way and enjoyable to review it, to check it. But in addition, we must to really remark that there were at least 3 more countries that were compromised, were engaged, were representing that in that contribution. Okay, so trying to do a little play with the numbers, we have 20 countries in Latin America, so representing the LAFRI strategy about 8, so it represents the 40% of representation. I think that, however, there are a lot of community that is not actually submitting contribution, but we already know as a colleagues and partners that actually working on it. So it would be a nice in advance in a near future if we can just try to really try to have an extra input on that sense. Okay, so regarding the balance between the experimental and theory was about 86% of experimental white papers. That what I think, or what we think that really represent what is the final goal of LAFRI, that is our experimental research focus on. But I think that the theory is a very important issue right here. Okay, so I think that only these numbers are representative in the sense that we must to really focus and be rigorous on what we can just analyze and evaluate afterwards. Okay, just in the sense that the contributions from Argentina was very nice. We had an interesting input from Andean for sure. That was our flagship regarding the most representative and likely large-scale research infrastructure in Latin America. Okay, homemade. and also contribution from the mathematics community, neutrino physics, even a nicely connection between these two topics. Another contribution regarding neutrino physics by employing nuclear reactors in in that setup. Okay, from the Colombian point of view, basically most of them were focused on DUNE. Okay, from the experimental and the theoretical point of view, and in the general context of the Colombian community. And this is a special case in Ecuador because it was not a strictly white paper submitted to the neutrino physics contribution, but a thematic area. But I identified that it was important to include it in this short report, this brief report, because the arrival of the CAIM-3 collaboration to Latin America early last year. Okay, so I'm going to really talk a little bit on it, but was not declared as a white paper. But I tried to adjust to this contribution. Okay, going to the contribution from Brazil was the large amount. Okay, the main I would say horsepower in that sense. Okay, and the several topics and involvements in not only technology or experimental point of view by theory and different approaches to the neutrino open question that we are going to comment in brief. Okay, uh, and finally, was interesting to really, in particular, for me to address this white paper because it's a very innovative concept to explore in the region where actually, to be honest, I'm not aware of that until I read this paper. Okay, there is also an important case I would like to comment on, emphasize on the line. It is with this white paper from the neutrino for the nuclear science in Brazil, because was not really identified as a direct contribution to the neutrino physics, but was very important to really know the update or of the reality we have actually and capabilities on nuclear science in Brazil. So that's why I tag it as declared but not adjustable, because probably that would be a very interesting discussion in another session of cross discussion. Okay, so neutrino physics in this symposium, as mostly of you know, we have several contributions. In that sense, there was two related neutrino topics yesterday covered by Guillermo and Ernesto. Okay, but however, I think that most of the white papers submit are represented in that section, unless the contribution of Nova. But I think that I'm going to spend a little bit more time on trying to contextualize what we are actually in that sense. So I really encourage you to go to the discussion session for an ample time on on the discussion and the doubts and inputs we can just really try to merge. I encourage you to try to really start to do it by the Slack channel. Okay, so this is only for an introductory point of view. Okay, that basically is what we all know about neutrino properties. Neutrino mixing, as we know, is governed by this PMNX matrix, which relate the mass agent state to the flavor agent states. So in that sense, we consider the if we consider the simplest approximation, the probability of a neutrino starring by a state called nu A, okay, is detected in a state neutrino B, given by this dependence of the baseline and the energy of the neutrino, and these are terms that we already know. But obviously, that is not the complete picture. That's the big picture of the neutrino properties in the oscillation case. But it's a nice representation of the data we're actually able to interpret. Okay, but if we want to go to going forward, it will not be longer sufficient, because if we are going to explore the lands of a new models and new physics, certainly this obviously has to be tuned in a such a way. Okay, in that direction. In addition, the PMN matrix is constructed as the product of three independent rotation, a unitary matrix, and the three mixing angle. We have different different experiments that were able to really help us to infer about the oscillation parameters. Okay, I think that this is the theory of the summary of the theory that was discussed by Carlos or presented by Carlos Wagner yesterday, but just as an introductory, as I say. Okay, so we know that from this contribution from atmospheric reactor and solar experiment, we can just build a PM index matrix of this way in terms of the sine and cosine terms. And just only to really be clear on what we already know, that the three mixing angles have been measured. We are really in a challenging state regarding the measurement of the CP violation violating phase. Okay, but away to this neutrino power meter, there are the four missing meter parameters. Okay, regarding to the delta time squared scales. Okay, delta time to 1 and delta time to 2. Depending of the way as we find this relation that we are talking about, normal hierarchy and the inverted hierarchy. In the inverted hierarchy, the delta m squared 3.1 and 3.2 are both negative, so that's an important thing that we are really challenging as an open question neutrino fixes still to be done. This is basically for neutrino properties, but what our current challenge regarding neutrino sources, that is other approach. Okay, that what this plot pretends to show is just to try to locate us as the function of which not experiment, which sources are able to be explored if we consider the neutrino energy we expect to really be working in as a function of the flux. Okay, so if we move to the energies in the range of the mega electron volt to the giga electron volt in this case, we probably will be approaching to getting the answer of the neutrino mass hierarchy with atmospheric fluxes. However, there are other components for other cosmic or astrophysical sources that we can be reachable or trying to give us an extra input of that ideas. Okay, as supernova neutrinos, or in a situation some lower energy component from AGNs. If we move further to the highest energy regime, okay, we can be talking about the giga electron volts and tera electron volts range, where most of the observable sky is known from gamma sources. And even a little bit more further on that, we are approaching to the highest energy regime, okay, of tera electron volts and beta electron volts sources. In that sense, I think that it's obviously important to comment what we have as reference, the ice cube signal of the TXS blazar and the astrophysical flux was discovered. Okay, so the question right now is what we are going to really approach through the experimental point of view of contributions, trying to solve or to use that information of that energy regimes or all the fluxes and energies, because we already know that we move to the physics field from from the oscillation experiment. We are talking that there are certain energy regime what is accessible for us, and above that energy, we are talking to really find the answers to the open questions is with the help of astrophysics and neutrino astronomy. But it's not only a matter of physics, because the detector requirements are also playing an important role, because if we move to a acceleration experiment, we already know that higher density is not required. And if we move to the astrophysical sources answer that are impacting on the larger volume design of the experiment. Okay, so after this introductory point, I think that really it's interesting to address the open question that was actually discussed yesterday briefly with Carlos' talk. And it's about the phenomenology. I think that if we want to summarize in a very educated way, there were two approaches. There are two approaches. The approaches from the neutrino properties point of view, and the approaches that we can do with neutrinos as a proof. Okay, so it immediately addressed to the question that we are really trying to pursue, okay, about the neutrino mass hierarchy, the CP violation, the neutrino mixing, the nature of the neutrinos, if it direct of Majorana neutrinos, how many neutrinos, and the role is actually playing the stereo neutrinos, and the absolute scale of the neutrino mass, and what can we extract from astrophysical neutrinos information. Okay, after the statement of the open question neutrinos, naturally we will be following the open solutions. What kind of experiments, what are they group in order to strategically pursue that open questions? So the neutrino oscillation experiments are able to cover some of the open questions we discussed previously. In addition, the remarkable neutrino double beta decay experiment and efforts worldwide, the direct mass experiments addressing to these specific fields, and also the role that are playing the current generation neutrino telescopes and neutrino cross-section experiments in the field. So this is only to really try to contextualize where we are in Latin America, because we are really involved with a large amount of experiments, or maybe not large enough at the US and the Europe, but I think that almost covering all the main topics on neutrino open questions, unless some of them related with the neutrino mass experiments. Okay, we probably know that actually there is an important contribution of the Colombian experiment through the next experiment in the Confront underground laboratory. Okay, but I think that in the other aspects we have covered most of the experimental techniques and an open solution to that open questions. Okay, we have a small scale projects that are remarkable, that are to very interesting progress, as the new experiment and CONNIE experiment, which are not a large scale but small scale, and even thinking about what could be really reach or find an agreement of the role can be the experiments play in the Andes facility. Okay, so now after the experiment addressing to that question, it comes the experimental techniques. So this is what is the basis of this report. Okay, we have identified that in Latin America there are mainly four experimental techniques that really are helping us to getting the capability, the strength, and the experience for local or large scale contributions. One of them is the scintillation and hybrid detector experimental techniques, the water sharing cup detectors, the radio sharing cup detectors, and the silicon pixel detectors. So we can say that neutrino hunting in Latin America is mainly pursued by four experimental techniques, addressing of the scientific questions I've already mentioned. Well, so that would be the driver of this contribution. Okay, obviously, this is not only a week about what we can do and what we are doing in the past and we are going to do in the future. That is also important, because in neutrino science and technology coupling to global strategies, we are actually working in a very huge and remarkable effort from Latin America in a very short way. Okay, in that sense, from the neutrino physics point of view, it's not the same as we just have a look to the snowman process in the US, mainly because we don't have the research infrastructure, neither the manpower they have. Okay, so that would not be probably enough proper to really address the goals we have from the typical topical groups that the US people has. But it's also but it's indeed useful for leverage of the process that we must connect, uh, strictly speaking, about Latin America, United States, and the European Union. Most of we know that the European strategy released an update some weeks ago, okay, where some of the points related to the neutrinos were encouraged to the progress on advanced research and development for detectors, accelerators, computing technologies. Well, and also the support of neutrino physics within different countries, different to the European Union, and also as cooperation with neighboring fields as astroparticles and nuclear physics. And this is an important the collaboration with not a European counterpart. So I think that we really be aware about the leverage point we must to find in this other global strategies. So the question right now about capabilities of neutrino physics and technology is the best way for addressing this. What we should follow. We think that integrally it is a merging of all the statements declared before. Okay, we must to go to the statement of neutrino open science, go to the open solution that actually in the worldwide are working in that direction. What is the neutrino technology and instrumentation capabilities we have in Latin America, and how do we couple to the global strategies? And indeed, more important is just what will be the sense in the long term or the midterm. Okay, from the European strategy, we agree that the technological application, the society, human capital, and environment impact is important, is very relevant in order to really have a consensus, to really find an agreement with funding agencies and even to the working environment of our nations. So in that sense, they underline, they emphasize on accelerated development detectors, computing, open science, and partnerships. I think that we should follow it integrally, take into account this scheme in order to find as possible an accurate or proper or strengthened uh, suggestions to the high level strategy group. Okay, I'm going to try to go a little bit faster. This is the capabilities of the summary we have identified in Latin America. As I mentioned, the scintillation and hybrid detectors is one of the as strengths that we have in our region. I'm not going to stop in details, but only to take a reference and to try to connect some key concepts on the technology we are able to do or to keep the force and going further in that sense. Okay, regarding scintillation and hybrid detector, we have the contribution of the JUNO experiment by Chilean and Brazilian institutions. Okay, basically we know that's a reactor experiment using the liquid scintillator sensitive detection media has a broad and ambitious physics programs. Okay, I tried to do it in a nutshell right here, but I'm not going to spend too much time discussing that because in the next contributions in this session are going to be addressed with more detail. Okay, but as we identify as main contributions in the June experiment were aimed to provide a better control of the systematic uncertainties on energy measurement. So we are talking in two fields, in two drivers, in two directions, either hardware through the small photomultipliers subsystem and some inherent systems of the JUNO detector as the underwater boxes and high voltage splitters, and indeed in software through the simulation board of the ABC boards. I'm sorry, to redundancy in that, and the data analysis from the software development point of view. Okay, if we move to the next slide, just go to where DUNE appears. Okay, probably is the most representative contribution and local or regional compatibility within the focus, within the contribution, within the local base or homemade initiatives, basically from the photo detection system for the DUNE experiments, okay, in the US, from Monte Carlo and physics from the standard model and beyond the standard model. I think that the most remarkable statement of that sense is the fact that probably the first time in Latin America history ever we have a big responsibility in the about to be in charge of the design and the commissioning of of a system of that size, okay, of that responsibility, and it is related with the photo detection system of the indeed, okay, for the for the fire detector. It is the so-called X-Arapuca concept. Okay, that's also an important contribution regarding the radar electronics, where the DUNE collaborators called Daphne, Daphne system, Daphne readout. Okay, for silicon photomultipliers as the main frontier with the detection of the ionization and scintillation signals in the type projection chamber. In the case of the software contribution, basically the force that we identify are focused in the Monte Carlo simulation for DUNE, and also very close in detail with the SBND experiment, also in the US, regarding the light production and propagation. And as the complete picture of the contributions of DUNE, focus to the physics analysis for beyond the standard model physics, non-interference direction, their mother and supernova neutrinos. If we move to the contribution of other remarkable experiment is Novi. Novi is what appears in our context from the contributions of the Colombian groups. It's not going to be unfortunately covering this symposium in this session, but as we already know, there is also a liquid scintillator experiment at the US, basically focused on the cross section for inclusion and exclusive channels for neutrino and antineutrino interactions. Okay, the main Latin American contributions are just focused on this topic, obviously.
Harold, you
But
have 5 minutes, okay? Harold?
okay, okay, Rogerio, thank you. Also aiming to try to find or to set limit on oscillation data. Okay, the main contribution we identified from the Colombian contributions, the Colombian support was the data analysis and reduction of alternatives for some specific physics implication of axial masses, finite iterations, and so on. Okay, after that, we move to the water sharing cup detector, probably the most experienced field where we feel that has a lot of things to really contribute to our local or global efforts on neutrino physics. It is a very important aspect that came through collaboration right to Latin America last year. So we are just trying to focus to the global efforts on neutrino astrophysical data analysis and neutrino and atmospheric neutrino data. It's a project that is under construction at the abyss of the Mediterranean Sea, has very defined programs at the identification and subsequent study of high energy neutrino sources, typical sources. Also going through the neutrino properties studies with two different layouts or two different optimizations. Okay, and even with an ambitious program that is actually taking place in Ecuador regarding to the calibration of the facility and the physics. Okay, other important large-scale water sharing curve experiment, which was identified, was Hyper-K. We know the importance of Hyper-K. Basically, this ambitious process, an ambitious continuity of the process followed by Super K. We already know that how huge were the contributions for Super K. Basically, it's a continuation of these programs, and from Latin America, which is the most important point, is the theoretical contributions. I think that this is an important thing that we must discuss along the symposium because I think that is also really interesting to see how could we reach the balance I mentioned at the beginning of the talk about theoretical and experimental side. There is the case of the Andean deep valley detector for high energy tau neutrinos. What I comment that is I think that is important. Is a really innovative, relative new for us. It's a concept that is supported by a lot of experiments and contributes worldwide. Even the IceCube Neutrino Observatory. Basically, we expect to reduce the uncertainty of neutrinos observation in the flat ground arrays by looking through the extension showers and trying to separate the components of the neutrino electron and neutrino tau induced cascades in the environment. So the physics program is very ambitious, is very wide. However, we still need to really try to get an input on what could be the address in the construction regarding the construction and commissioning of the physics also involved. I'm not going to stop in this part of the neutrino experiment because I think that we really received enough information from Ernesto yesterday. Okay, so then I move to radio sharing curve detector. It's another important aspect to comment because it's another technique, probably not familiar enough for most of us. But I think that it's important to really explore the capabilities, for instance, for the highest energy region in the neutrino flux astrophysical flux spectrum. Okay, there's a different technique, different approach that we also can combine with proposals of progress on water sharing of experiments. I think there are a lot of engagement and covering most of the principal working aspects of the commissioning for the experiment, not only from the hardware point of view, but computing, but physics. Okay, silicon pixelate detector were reviewed by Guillermo yesterday, so I'm not going to stop in either in that sense, but only to really introduce what is going to be presented by Rena in CONNIE experiment. We know that also share the CCD technology with a neutrino angle experiment. Okay, this is already running from 2016, basically focus on the coherent Neutrino-Nucleus interaction cross-section. As we know, that's a standard model prediction, but never measured, so that was a very interesting physics program that is worth to pay attention it's worth to pay attention enough. Okay, also trying to expand to other concepts and even to applications or practical roles of neutrinos in nuclear security applications. Okay, I'll only try to summarize with this chart. Probably it's not accurate enough, so I apologize in advance if it's not. But I think that nicely summarize what could be the decision points in order to really explore the highest impact of our collaboration actually in the region. Okay, from the capability building, the scale of the experiment, the research and development, delivering instrumentation that different contributors and countries can just give to the field, and the multiple regional involvement, that is a really important discussion point that we must do take a little bit more attention. So finally, discussion of recommendation. I would like to really encourage you again to try to merge or try to focalize the discussion through a Slack channel. Okay, mainly through that drivers, because it's going to help us a lot to give a big picture of the idea to raise to the high level strategy group. But it's only an appetizer for sure. We expect a lot of diverse contribution and point of view and discussion and comments. Okay, so that's all of, I wanted to be comment in that sense. And we expect to have at closing of the event a big picture that can be represent all of our winter of all of our interests in our countries, in our regions, and the recognition of our work and contribution to the field worldwide. That's all for now. Thank you.
Thank you very much, Harold, for this very nice summary of all the white papers. And now we will go directly to the white papers. So there's only one question in Slack. So you mentioned Sensei, and Nicolas is asking who is actually involved in the Sensei collaboration. Guillermo involved?
Hello, yes, I'm involved. Perhaps that's an interesting, that's a dark matter experiment, but it's an interesting experiment if you think in the deep underground Andes laboratory, right? That should fit there perfectly. So I think in that context, it's great to have it there, yeah.
Yeah, but are you actually involved in the Sensei collaboration?
I'm involved in the Sensei collaboration, yes.
Thank you very much, Guillermo.
Yeah. Nice.
So Harold, I would like to ask you to keep moving the slides for the following speakers. So you should have all the all the presentations in this file. So if you're just going through the file, you see all the presentation.
You catch me? I don't really remember where is it.
So there was a big file. Okay, I'll do it. Don't worry. I'll do it. Okay.
Okay. Try to move faster. Okay. All talks right here. Okay. So.
You found it, or?
I think that yes, but it's spending too much time. Okay,
Yeah,
please.
It's a long file, so
a little bit patient. Sorry? I'm trying to find it. Okay.
Don't worry, I'll do it then. Don't worry, I'll do it.
Okay, you can do it, maybe.
It's in the beginning.
Because I'm late with that. I don't know where is not actually here.
Are you actually looking at my screen now? So you can see the talk.
You're already there.
Okay. So the next speaker then is Hiroshi Nunokawa. He's going to talk about the Hyper-K effort. So Hiroshi, I just moved the slides for you, okay?
One moment. Can you hear me?
Yes.
One moment, yeah. Are you showing my slide?
Sorry, I was supposed to show your slides.
Yeah, I couldn't see that.
Sorry.
Yes.
Okay, thank you. Yeah, okay. So can I start?
Yes, please.
Okay, so I'd like to thank the organizer for giving me this opportunity to talk about a bit about Hyper-Kamiokande. So let me go. So first, let me try to make a brief introduction about Hyper-K. So next page, please. So what is Hyper-Kamiokande? So Hyper-Kamiokande is the next generation large-scale water chemical detector. And it's also at the same time, it's associate name of the associated physics project. Just to know how, tell you the idea that it is the successor of Kamiokande and Super Kamiokande, about 8.24 times larger than Super K.
Oh, sorry.
Sorry, yeah. Okay, so next, please. Next slide. Yeah, so current status of Hyper-K is the following. So it is officially approved in Japan, and it already started to the construction. It is under construction and to aim to start operation in 27. Yeah, so next please. However, the Hyper-Kamiokande doesn't have yet the official collaboration. It is still called the Hyper-Kamiokande proto collaboration. So Hyper-K is now in the transition phase. It's going to transform into the formal Hyper-Kamiokande collaboration at some point. Roughly speaking, so about 400 members from 18 countries currently are in the proto collaboration. So next, please. Yeah, so I just would like to highlight just three topics. So one of the physics goal, one of the important physics goal is long basin oscillation physics, and in particular the observation of CPU violation. The idea is just idea is very simple to compare by comparing the oscillation probability of the nu mu and anti-nu mu, nu ma, neutrino and anti-neutrino channels. And the next slide. Yeah, so this is the canonical plot to show the sensitivity, which have been shown many times in many conferences. Also, the DUNE experiment shows something similar. I would say that sensitivity is comparable of Hyper-K is comparable to DUNE. I think. Sorry. No, this is not a. Yeah, next, okay. So next, yeah, this is a CP vibration, no? So also the Hyper-K has another important goal, which is the nucleon decay. Just because of the larger physical volume, roughly 10 times or 8 times, larger than the super K, the significant improvement on the current limits can be expected. This plot shows just two major decay modes predicted by many theoretical models. So both, especially the proton goes to E plus and pi zero, the Hyper-K can be the world-based, can provide world-based limits. So next slide. Another important programs of the Hyper-K is neutrino astrophysics. Just due to the lack of time, I just mentioned only one. Observation of galactic or nearby supernova neutrinos is will be a spectacular event we expect to happen in the next decades. So for this is important, very important, since we have only one example in the past neutrino observation from SN87A. The next galactic supernova, if observed neutrino, if observed, this will help a lot in terms of theoretical interpretation or understanding the supernova explosion and also the formation of neutron stars and black holes. So next, please. So okay, let me. So this is a timeline, official timeline, current official time schedule of the Hyper-K. So we started the construction. It is under construction, and then if everything go well, 27. We aim to the Hyper-K aims to start operation to take data. So next slide, please. So what is the contribution? So currently, in fact, compared to DUNE efforts, we are very minor. We are a minor group. So currently, we are only 3 people, just 2 faculty members and 1 postdoc from Rio de Janeiro. So I put my name and my Smiley, Alexander Quiroga, postdoc. And though I don't have direct contact, recently, I know that there are some groups from Mexico joined Hyper-K, though I don't have direct contact with them. So currently, there are 2 groups from Latin America, if I include Mexico. So because we are theorists, our contribution, we are thinking currently at this moment, we are thinking mainly the theoretical contribution. Next slide, please. So possible contribution, no, we are thinking is because as I said, since we are theorists, we are considering so far the more theory or analysis oriented contribution. And we would like to explore as much as possible physics potential Hyper-Kamiokande, to prove some new physics, no? Especially we are interested because CP violation sensitivity or mass ordering sensitivity, etc., already explored to a good extent. So we are interested to prove some new physics, not expected in the standard model plus just 3 massive neutrinos, such as decay, star neutrino, non-standard interaction, etc. And also we are interested to explore some non-trivial synergy between Hyper-K and the experiments such as DUNE and JUNO. Here, what I mean synergy is not just inclusive statistics. By combining 2 experiments or more, it would be nice to see some complementarity, and non-trivial synergy. Yeah. So this is also we are interested. So in this sense, we are interested to also interact with the other groups. And also, depending on the financial situation, maybe we can try to make some small contribution to the computing and storage through grid. If this also we are thinking. And next, please. So this is so yeah, just as an example. No? So we are now working on the decay scenario, testing the decay scenario by using the second, in fact, by using the 2 detectors, because Hyper-K has a possibility. It's thinking about the possibility to put second detector in Korea, because the JPAC beam will pass Korea for free. So in principle, we can try to use this beam also by constructing second detector. And then just as an example, we are studying currently preparing some paper which studied the neutrino decay. So just because along our baseline, and we expect some impact in the far detector, in second detector in Korea. This is in preparation. So next, please. So this is not our current, we don't have current any definite plan because we are theorists, but if there are some new participation from Brazil or nearby country who are, experimentalists, no? If there are some people who have some experience in hardware instrumentation, in principle we can try to make some contribution also to the hardware. Yeah. Okay. So next, please. I think the final. No. Yeah. So just to conclude, so we are theorists. I am theorist, but it's clear that no real progress can be made without new data coming from new experiments. So experiment is very important, I think, and Hyper-K, we believe that, I believe that Hyper-K project has strong scientific motivation and good prospects to obtain some new significant results. And we believe that, I think that I believe, or we believe that collaboration or interaction between theorists and experimenters can be very critical in principle. So, and also, as I mentioned, it would be interesting to consider complementarity and or synergy between the different experiments, not just between Hyper-K, any experiment, some synergy between any different experiments. And new participation is always welcome. So thank you very much.
Thank you, Hiroshi. So Haro, do you have the file now? Because I think it's better for you to.
I already have it, yeah. It takes a lot of time, but I already have, yes. Okay.
Because for me, it was difficult to coordinate everything. So
okay. Yeah, sorry. Sorry, that's my fault. Yeah.
So the next speaker is Romero-Wolf, and he's going to talk about the Andean deep valley detector for high-energy tau neutrinos. So hopefully you have these slides.
Okay, so we are actually right here. Okay.
Yeah.
Hi.
So Andres?
Yes. Can you hear me? Hello?
We can hear you.
We can hear you. You can go ahead.
Yes. Hi. I'm Andres Romero-Wolf. I'm a researcher at the Jet Propulsion Laboratory and California Institute of Technology. And I would like to thank the organizers for inviting me to give this short presentation. Next slide, please. So the motivation for this is where we are, is IceCube has discovered a astrophysical flux up to 10 PeV. The result is now way above the discovery threshold of 5 sigma. IceCube has excellent muon neutrino identification, but from the latest results that I've seen, their tau identification flavor is still consistent with background. And the main method which they use to identify these taus is you have a tau neutrino interacting, producing a hadronic shower on the bottom left. A tau is produced, which propagates, leaving Cherenkov radiation along its track, and then it decays, producing a second shower. So tau neutrinos are a critical messenger for interpreting properties of astrophysical objects and searching for new physics. And we had 2 neutrino white papers, of which I was a key member in developing for the Astro 2020 Decadal Survey. So the question that arose during this process was, can we build a detector that is more sensitive to high energy tau neutrinos, specifically that overlaps with the IceCube energy band? Next slide, please. So this is the basic idea. This idea is actually not that new. Daniele Fargione proposed a version of this in the 1990s in an ICRC proceeding. But essentially, when we're looking at what kinds of detectors would be favorable for tau neutrino detection, we sort of rediscovered this. And the basic idea is, if you're in a deep valley, you can have a tau neutrino interact in the mountain, which produces a tau, and the tau itself has a range of 50 meters to 5 kilometers, depending on the energy. When it enters the deep valley, it decays, producing an air shower. And the reason this is, well, so it's favorable for taus because of the geometry. Of course, the Pierre Auger Observatory uses essentially the same idea, except they're on flat ground, and the mountains available to them are too far away to really contribute significantly to this channel. So it's basically a geometric effect that gives you the gains here. And in addition, the mountain shields against other backgrounds. So in our initial study, what we found was that you can still have muons produced by this interaction and escape, but the muons do not decay in the length of that deep valley, whereas the taus do. So essentially, when you consider all the possible effects, at least the ones we've considered to date, the ratio of tau neutrinos versus muon taus that produce a signal is 20:1. So it's by neutrino physics standards a very high signal purity for tau neutrinos. Next slide, please. So why the Colca Canyon? We identified about 4 very deep canyons, right? So you want them to be several kilometers deep and maybe 5 to 10 kilometers wide, because that matches the tau range at the energies of interest. And there may be more, but there are 4 known canyons that have this, well-known canyons that have these features. But where the Colca Canyon stands out is that it's already populated. It's not a nature reserve like some of the other canyons that we mentioned in our study. It has road access, and it has towns, and it has some amount of infrastructure that we could build off of. And of course, it has water at the bottom of the river, which is really useful for building the water Cherenkov detectors. And that's experience developed from building the HECAP detector in Mexico, and the costs of trucking the water to the detector site in construction. Next slide, please. So this is the expected performance. So the way we sized this was, we said, well, we want to match IceCube sensitivity at 1 PeV, include a factor of 3 for the different flavors. So what I'm showing in the plot of the left is the acceptance versus the energy. The IceCube new tau flavor is shown in the thick black dotted lines. We sized it using a 1 PeV and basically tripling the acceptance to see what was needed. And then the blue line is the expected performance from simulations, and the dashed line is just if we had a perfect E energy power law scaling. So it does pretty well at a PeV. It even gets you down to a few hundred TeV, where backgrounds are start to dominate, and it shoots up to in sensitivity at higher energies. And I've put a version of IceCube Gen 2. There are several talks out there. This one's from a TEFPA 2016, just to get a sense of how it compares to the IceCube Gen 2 all flavor sensitivity. So it's it has the potential to measure the tau fraction at PeV energies and actually get a significant sensitivity at higher energies. It's rather ambitious in size to meet this. It's about 30,000 cubic meter water detectors, so not quite as large as the ones used for Auger, which are more like 1.2 meters by 2 and so meters. So that they're smaller, but more of them are needed. The expected event rate using one of the conservative fluxes from IceCube is about 21 events per 3 years, which is roughly what you would expect to get a 5 sigma discovery on the taus. Of course, with something 4 times smaller and maybe waiting longer, you could still discover the tau astrophysical flux and then build up your statistics that way. So it's a trade of how long do you want to run, how much of the site is actually accessible for construction, and other considerations. So this is still an early concept, and we're figuring out its feasibility on various fronts. So next slide, please. So these are the science objectives, which were actually mentioned by Harold before. So we want to see whether the spectrum, neutrino spectrum, continues above 10 PeV. We want to characterize astrophysical sources in the flux between 1 to 10 PeV by measuring the tau component. And of course, this also serves as a multi-messenger facility for detecting neutrinos with transients. So upcoming developments, in our report, we put sort of our 10-year plan. What we're doing now is finalizing the detector studies over the next year, using more detailed simulations and the like to make sure we've understood our backgrounds and the sizing of our detector. We want to initialize prototype design for next year, so we have something to propose, and essentially develop a construction strategy to optimize science return as a detector is being built.
2 minutes.
Okay.
I think this is the last slide.
Yeah. Okay, thank you.
Oh,
so
yeah.
Harold, I will be chaired. So thank you, Andres, for this very interesting talk. I'm sure we have discussions about this in the discussions, more talk. Yeah, we should discuss this project. Next is Irina. She's going to talk about CONNIE. So Irina, can you start, please?
Yeah, thank you. So I will talk about the Coherent Neutrino-Nucleus interaction experiment, which is situated next to the Angra 2 reactor near Rio de Janeiro, Brazil. If you go to next slide, please. So we are a small international collaboration of around 30 members from these countries and institutes. And differently to what I saw in Harold's table earlier, we are actually a regional collaboration. We are a multi-continental collaboration, if you want. And the great majority of scientists involved are from Latin America. So if you go to the next slide, please. So the main goal of the experiment is to detect the coherent elastic neutrino-nucleus scattering of neutrinos in silicon nuclei, and also to put limits on models beyond the standard model. As we know, the process is difficult to detect because of the very small energies of ionization involved. The process involves the scattering of a neutrino of the nucleus as a whole. It's a neutral current process. And for the detection, we use scientific CCDs with high resistivity and large thickness, especially developed, that are also used by DES and DAMIC. One CCD is 4,000 by 4,000 pixels. And with these, we managed to achieve a very low energy detection threshold of around 40 electron volts and low noise. Next slide, please. So why are we interested in this measurement? The coherent scattering process is very well predicted in the standard model, so any discrepancy that we measure can be interpreted as a sign of contribution from new physics. And there are several new physics models that predict such large enhancements. For example, the non-standard interactions of neutrinos, which are mediated by, for example, dark photons. They can be mediated by new vector scalar mediators. Also models with sterile neutrinos, models with an anomalous neutrino magnetic moment. And the process can also be used to probe neutrino oscillations at low energies and very short baselines. Outside of new physics, the process is also very important for direct dark matter searches as it's an irreducible background. And it's relevant for the models of energy transport in supernovas. And finally, once the detection is well established, it can be used to create compact detectors for reactor monitoring in a non-invasive way. And our experiment was quoted in the conference Science and Global Security with this in mind. And next slide, please. So the CONNIE experiment is located in this container lab adjacent to the dome of the Angra 2 reactor. We share a lab with the Angra Neutrinos project, as we heard yesterday from Ernesto Kemp's talk. The reactor has a thermal power of 3.8 gigawatts and gives us a flux of about 10 to the 13 neutrinos per second per centimeter squared at the position of the detector. We are 30 meters from the reactor core. Next slide, please. Okay, so first, the first prototype, detector prototype, was installed in 2014, and then the scientific CCDs were installed in 2016. And you can see on the left a copper box containing the CCDs parallel to each other. This is installed inside the dewar, which keeps vacuum and low temperature. And you can also see the several layers of shielding that protect from neutrons and photons. If you go to the next slide, please. So after 2 years of running, 2016 to 2018, we published the first results, and that comes with an active mass of about 50 grams. What we look at is the energy spectrum of events with the reactor working, with the reactor on, and with the reactor off, and we compare these two spectra. And the difference between the two in the bottom left plot is compatible with 0. So this translates into a limit on the coherent scattering event rate. Currently, our limit sits at 40 times the prediction of the standard model. So if you go to the next slide, please. So even though the limit is at 40 times the standard model, this can translate into stringent limits on models with new physics. So we looked so far at a model with a light vector mediator Z prime in the bottom plot and a light scalar mediator phi in the top plot. And you can see that in the red region, we obtain the most stringent limits for low mediator masses of below about 10 MeV. And these results were quoted at the Neutrino 2020 conference in the Raymond Strauss's review talk as a community milestone. So this is the first competitive beyond the standard model constraint from a coherent scattering at reactor neutrinos. Next slide, please. What is the current status of the experiment? We are running continuously. Since the last results, we implemented the hardware binning of the data, which reduces the effect of readout noise at low energies. We've also implemented several improvements to the analysis techniques, and this is new since the white paper submission. So we have new calibrations of event size versus depth and of energy, and we have a revised neutrino signal selection. We also managed an improved control of backgrounds, where the low energy background is better understood now and reduced. And we are monitoring muon rates using a new tool and observing them to be very stable. So we plan to publish this analysis later this year. And as a whole, in the past 10 years or so, CONNIE has developed greatly the Latin American expertise in reactor neutrino experiments. This is both at the level of instrumentation and also data analysis. And we've had a number of postgraduate and undergraduate students involved in the experiment, 14 postgraduate theses and 9 undergraduate projects and between the past and current ones. So we are training new specialists in the area in Latin America. Next slide, please. So what are the plans for the future? Our plan is to upgrade CONNIE with new skipper CCDs, and we heard about them yesterday, so I won't repeat this. We heard it in Guillermo's talk, but they bring about a great reduction in electronic noise and are very promising technology. You can have single electron detection with them. So if installed at CONNIE, this will reduce our energy threshold by basically an order of magnitude. And our preliminary studies show that we will have a greatly improved sensitivity. So here is the black line is the current CONNIE sensitivity. The blue line is if we install a skipper. And the red line is the possibility to put CONNIE closer to the reactor core, so inside the dome at a position of 15 meters, which is the same position as the CONUS experiment. So this is an important possibility, and we are exploring it currently with the electronuclear management. Next slide, please. And this is my final slide. So we plan to upgrade CONNIE next year with skipper CCDs. This will bring an increase of up to 6 times in the neutrino rate. This requires a new quenching factor measurement for lower energies, and this is an ongoing effort also outside the collaboration. In the longer term, it's fundamental to create a larger mass kilogram size reactor neutrino experiment with skippers, and that would require a new infrastructure in Angra 2 to accommodate a bigger experiment. Also, a major challenge for such an experiment is understanding the reactor background, and we are working very well on this. And we also participate in a wider effort, as you will hear in Guillermo's talk in a bit. In any case, an upgraded CONNIE with skippers will act as a pathfinder for any future large-scale experiment, because we have a very well-known background environment, very well-known operation and stable operation, and it's a very well-working experiment. And it's not an exaggeration to say that CONNIE is currently the most significant particle physics experiment in Latin America. And this puts us in a unique position because we have the expertise, we are training new specialists, so we should take advantage of this and further our efforts to realize the full physics potential of the experiment. Thank you.
Thank you, Irina, for this very nice talk on coherent neutrino scattering and CONNIE. I think there will be lots of discussions in the discussion session, especially because they're sensitive to neutrino anomalous magnetic moment, which became very fashionable since last week. Thank you again. And so next one is Pietro Chimenti, who's going to talk about, oh, sorry. Something
Hello,
happened.
no, I think it's me.
Sorry, the program. Oh, I'm sorry. No, you're right. So it's Moreno. He's talking about DUNE.
Yes.
Sorry about that.
Yeah, don't worry. So just first of all, I want to thank you to the organizer for giving the opportunity to talk about of this work that Colombian institutions are doing in the DUNE experiment. So in particular, okay, so my name is Davis Moreno. So I am working at the Andean University, and together with the Universidad Escuela de Ingeniería de Antioquia, we are participating right now actively in the design and the design of one of the components of the DUNE experiment. So next slide, next slide, please. So thank you. So just to put into context the work that we are already doing in DUNE, I just want to mention that DUNE is a long baseline neutrino experiment where a powerful neutrino beam will be produced and Fermilab and focused to the far detector located 1,300 kilometers far away of Chicago in South Dakota. In South Dakota, the far detector will be is under construction, and the far detector will consist of 4 big, massive cryostats filled with liquid argon. 2 technologies are considered for the far detector: the so-called single phase and the dual phase. In particular, the single phase consists of a cryostat completely filled of argon in liquid state, where for the detection of the neutrinos, a time projected chamber will be responsible for the collection of the charge producing when the neutrino interact with the argon. So the time projected chamber consists of cathode and anode planes, so with a electric field to collect the ionization charge. Additionally to that, and very important for us, is the photon detection system embedded in the TPC that is responsible for the collecting the photons producing at the first interaction of the neutrino with the liquid argon. As already Harold said at the beginning of this session, the photon detection system is very important for Latin America because it's based on one concept developed in Brazil, the Arapuca concept, that is very useful to collect a large amount of photons produced during the interaction of the neutrino. And in particular, the Colombian institutions that I already mentioned at the beginning, are working on the readout electronic for the processing of the signals collected with the Arapucas. So next slide, please. So the electronics for the detection of this of the processing of the signals collected by the Arapucas is called DAFNE. DAFNE means detector electronics for acquiring photons from neutrinos. In the collaboration, it is also mentioned as the warm readout electronics for the DUNE single phase. These boards, these electronics, is development between a collaboration, sorry, between Latin American institutions and Fermilab. So it is based on a previous concept called the MUTUI experiment, and the development of these boards is as I say, this is a partnership between Fermilab and Colombia and Peru initially. And as you can see, the last autumn, one of the professors of the Andean University was in Fermilab working on the design of the DAFNE boards. Also, the engineer Juan Vega from Peru was there working also on the design of the Daphne boards. Next slide, please. So here we can see some general characteristics of Daphne. So the left column presents the main general design guidance for Daphne, based basically on the physics requirements of the experiment. The middle column presents the hardware itself, the PCB of the Daphne boards that, as I say, were developing with help of the Fermilab electronics group. And as you can see there, there is a strong collaboration between different Latin American countries in the hardware part, no? The Antonio Nariño, the CONNIE in Peru, and also the Fermilab collaborators. Additionally to that, for the firmware and software, you can see the main characteristics in the right column. And you see that also this firmware and software development is a work that is ongoing between different countries in Latin America, involving Peru, Colombia, and for the communication with the external data acquisition system, the Paraguayan group is also working in this part of the firmware. So we can move to the next slide. So in the white paper, so we wrote some ideas of how we think we can move forward to follow with this development of the Daphne board. So until now, we are doing, I will say, a very impressive work in the design and in the software and firmware part. But of course, we need some additionally input, and we think that one of the ways that we need to improve and go forward is keeping this innovation policy into the political agenda. I think this is one of the main objectives that we think are primordial for the development of the experiment. Also, we think that making a strong communication between different groups, between different institutions is also very important in order to improve the participation of other countries and other institutions in this kind of experiments. So there is a lot of work to do, and I think that we in Latin America, we are able to produce, to do that work, perform that work. We already demonstrate that this is possible. So, but also we need to try to increase the communication with the industry in order to make the transfer of technology more a larger transfer of technology between the community, scientific community, and the industry. So, in the next slide, please. So just to finalize, I just want to remark that the DUNE participation, Latin America participation in DUNE, and specifically in the photon detection system, is a regional program, I will say. We have different institutions working in different aspects of the Daphne board specifically, so with the electronics, hardware, firmware, and software, there is plenty of room for more participation of other countries. As a general schedule, I will say that the first Daphne prototypes are planned to be produced this year. Of course, due to the the COVID situation, we have a delay on the schedule, but still we are on the way to get the first Daphne prototypes to be tested in Latin America. Also, the next year it's planned to send some of Daphne boards to CERN to be tested and prototyped. Two, and as I say, there is plenty of room for more Colombian and Latin America participation in this effort of the hardware for the readout for the photon detection system. And I just want to finalize with this last bullet, that we think that the participation of in DUNE experiment is an unprecedented opportunity to make a contribution of great responsibility at the regional level, and also to understand how can we coordinate between different countries in Latin America. Thank you.
Thank you, Davis, for this very nice talk. So I'm sure we're going to hear much more about DUNE in following talks and also in discussion session. Thank you. Next is Pietro Chimenti. He's going to talk about JUNO.
You hear me?
Yes.
Okay. So good morning. First, I would like to thank you, the organizers, to let me talk at this meeting. And I would like to start discussing the people in Latin America involved in the JUNO experiment, because the group is not very large. Are four people with a permanent position at university, and two are engineers, two are physicists, mechanical engineer, electronic engineer, experimentalists, and theoreticians. And also I included the technicians and engineers who are helping in the development and construction of the small PNT system. I will talk later. And also I included Pedro Shoa from California, who is still retaining a visiting professor at PUC Chile. So I think there is a nice group integrated with people with different expertise, and very well supported by the international community, both in the United States and in Europe and in China. So I think this is a nice group. Next slide, please. Okay, I would like to, since this is a strategy discussion, I would like to highlight this my view on this point. I mean, reactor neutrinos, you all know, provided landmark results. The first detection of the free neutrino, and then in the Camland experiment for the explanation of the solar neutrino problem, the measurement of the θ13 mixing angle, and South American institution has invested a relevant amount of resources, not only money, but time of people and infrastructure, participated to these worldwide experiments. So I think that if we want to build the next landmark experiment in South America, and I still think this is the dream for most of us, then I think we have to participate to today most important reactor neutrino experiment under construction. So I think this is strategically extremely important. Moreover, this is not, although some physical goals are similar to other experiments, this must be considered as a complementary project with respect, for example, to DUNE or other long baseline oscillation experiments. So next slide, please. Okay, the JUNO collaboration is a relatively large collaboration with four institutions. Okay, next slide, please. Four institutions from South America. Next slide, please. The physics goals, I think this has been already discussed in the introductory slide presentation. So just quickly, of course, the most important is the determination of the neutrino mass ordering, and there is a race between different experiments to be the first to do that. However, we should highlight not only the competition, but also the complementarity between different strategies. Also, very important are the precision measurement of oscillation parameters and the supernova neutrino, for example, and other exotic searches. Next slide, please. Okay, about the location is very lucky. I mean, to have two sites, extremely powerful power plant, exactly at the right distance from a mountain with a very good quality of rock, where you could build the JUNO detector, has been a lucky situation. I would like to mention also that the JUNO tau detector, which is a detector to be constructed near the Taishan nuclear power plant, will be very important in understanding the final structure of the reactor neutrinos. This should not be considered as a near detector in the sense of the double show detector, right? That has two identical detector, one at about 1 kilometer and the other one closer to the power plant. This is a detector to understand better the antineutrino spectrum, but it is not a near in the sense that is not identical to the far detector. Okay, next slide, please. So the detector is, because of the physical requirement of statistics and energy resolution, this is a very large detector of about 20 kiloton of liquid scintillator plus the Bertou system, which is of ultra pure water. And I would like to stress also that it must have unprecedented energy resolution because of the necessity to observe the ripples in the spectrum to determine the mass hierarchy. In order to do that, the 77.5% coverage of the full detector in active multipliers must be achieved. And this has been achieved by employing two types of multipliers: large multipliers of 20 inches, which guarantees most of the coverage at an acceptable cost, and the smaller 3 inches for two multipliers, which allow to work a different in a different regime, so that we can cross-check the linearity of the measurement. So next slide, please. Okay, so this is the concept of the small photomultiplier system. So you see that small photomultipliers of 3 inches are placed by the larger one. So the idea is that while, for example, if we have an inverse decay produced near the edge of the active detector, there will be a large photomultipliers which will receive most of the light, and this could make difficult the exact measurement of the amount of light produced in the active detector. On the other hand, these small photomultipliers always work in a single photoelectron regime or very close to it. Of course, correction must be taken into account, but this will be second order effect. So the small photomultiplier essentially provide a very important tool for the energy scale precision and the understanding of non-linearity and non-uniformity within the detector. It is important that European and institutions from the United States are taking a leading position on that, and we are involved with this within this group, and very well organized within this group. Okay, so next slide, please. Okay, so the hardware contribution essentially is we have both mechanical part, which is the underwater box. Essentially, this is the box where the electronics must be put inside the detector. And this is a delicate piece because once the detector is commissioned, it will have to stay stable for decades. So there are strong requirements of the mechanics in terms of stability over time. The same thing can be said for the electronic pieces. In particular, the Charlie University is also developing the high voltage splitter, which will distribute the high voltage to the photomultipliers. On simulation and analysis, we are essentially involved in two, three things. So one is the electronic simulation. So in order to have a complete description of the detector within the G4 simulation. Then
Pietro, sorry, you have to wrap up. Can you go?
Essentially finished. Next slide, please. Okay, next slide, please. So the milestone is a very tight time scale with starting to take data from 2020, ready to take data from 2022, and conclusions. So from institutional point of view, JUNO is in process of being recognized by RENAFI. This is very important within Brazil. And also it has been partially funded by CNPq, FRAPERJ, and ANID. And I mean, this is a great project, I think very important for South America. So it would be nice to have more people involved. Thank you.
Thank you, Pietro. Sorry for being harsh, but we have to move on. I just want to remind people that you can write questions in the Slack Neutrino channel, so that we can start with these questions in the discussion session. Also remind you that there's a sign-up sheet. It's nice to see who is actually attending. And right. So next talk is Guillermo, or Guillermo, as Marcela likes to say, Fernandez Moroni, and he's going to talk about short baseline neutrino experiment, nuclear reactors and skippers.
Okay, hello again. I'm trying to find one of these lines to draw. Okay. So yeah, I will talk about this new experiment, right? That is at the very beginning stage, that is called Violeta, right? I'm on behalf of that collaboration. So when we wrote the white paper, the collaboration was starting in Argentina, and now we are a broader scientist community, which is in Latin America. And of course, this is very related with what Irina showed before, right? The CONNIE experiment. But this is just focused on how we can use the skipper detector, right? When you have a reactor experiment, the main limitation of that experiment is the background, right? The cosmic background. And in our case, for the skipper CCD, if you go to the next slide, please. In our case, for the skipper CCD, our threshold is around a few EVs, right? A few deposited electron volt of energy, right? Compared to 150 electron volt that you can see in the CONNIE experiment, right? So these are 2 orders of magnitude in energy deposition, and now that you have the resolution to observe those small amounts. So that's why this was essentially the motivation for this new collaboration, just to have a solid group of people just looking at the skipper and trying to understand how the skipper works on this context, right? So I will essentially tell the story again for the skipper, but now in the application of detecting neutrinos, right? As I tell you yesterday, the skipper CCD is a sensor that can discretize or can read the ionized charge in silicon in a discretized way, right? So you can essentially count how many precisely, without any error, how many electrons or electron hole pairs have been produced by a given interaction in the silicon bulk, right? And this is how it looks like when you put the detector sorry, when you put the detector in a light tight environmental, you see an image that looks like this, and you collect muons, but more importantly, you see these small dots that are a single electron hole pair production in the bulk of the sensor. And that's the kind of interaction that we are interested in this application, because we want to push the threshold of our sensor to very low energies, right? So that's the key aspect here. If you go to the next slide, please. So as I was telling you, this is a collaboration that is distributing in Latin America. This started in Argentina because of two reasons. The first one is that Argentina, from the very beginning, the development of instrumentation, the sensor, and the understanding of operation of the sensor together with Fermilab 10 years ago. And that's why it has a lot of expertise already developed there. I explained it a little bit more yesterday. But after that, I mean, there are also other institutions that have been used the sensor in the last year, and now this expertise coming from Fermilab or from Argentina is being distributed in Mexico, for example, that is doing the development of theory of the absorption of related with the absorption of energy related with the quenching factor for very low energy depositions, Rio de Janeiro also for the operation of the sensor, and Paraguay with simulations at very, very low energy scale, right? So this is more or less this slide to summarize what are the main contributions that have been around or have been produced by Latin American institutions on this particular topic. If you go to the next slide, please. The second reason why there are a big community in Argentina pushing for skipper in reactors is that there's a large community or a large groups doing nuclear physics in Argentina, right? Argentina not only operates nuclear reactor for power and isotope production, it also fabricates reactors. So it has a large number. If you look at the image on the right, you see the history of Argentina building and operating reactors. You can see the distribution of reactors in the country. And for this particular project, we have divided these reactors in two groups. One that can be used, that are already open for research, that can be used for, these are research reactors that can be used for R&D of the skipper. And they are already open, and you can place the detector very close to the core. And this is a small core, so it allows you also to use it as a sterile neutrino experiment, right? Because you don't have the phase washing if you have a very large core. On the other hand, we have the power reactors, right? Like Atucha 2, where is the place where we want to put the first prototype, the first skipper prototype, right? And the reason why we are pointing to Atucha, we have that Angra is also available, but we want to try to use Atucha because we have already visited the plant 2 times, and we have selected 2 locations that are very close to the reactor. We have been around, we have been in those places, and especially there's a square here where the fission takes place, and these locations are at 8 and 12 meters. So it has 2 contributions. The first one is that you are inside of the building, so you have some overburden. And the second one is that you are closer to the core, and you have a higher flux when you compare to the Angra lab. So that's essentially why we are trying to push for this particular location. But apart from that, I mean, I should mention that nuclear reactors are the largest or the most intense source of neutrinos in the world, and we have a lot of them in Latin America, right? So, and we have a sensor that is able to look at those neutrinos. That was the reason why these neutrino sources were not used in the past, right? So I wanted to make that point. I mean, doesn't matter what would be the final location. I mean, it is very important that we push for using these machines that are already in Latin America, right? So if you go to the next slide, please. This is so we have an experiment that is called Violeta, and a collaboration that is called Violeta. It means Neutrino Interaction Observatory with Large Energy Threshold Array, and the idea is to build a multi-kilogram array of skipper detectors. So if you look at the plot on the bottom left, you can see now where these places that we want to use for the experiments are in Atucha, right, where the neutrino generation takes place. And we have also a prototype running at Fermilab. We are making studies in the background in this new energy regime, right, up to a few EVs, and trying to adapt the current simulation tools for this very, very low energy. And we have already held our first workshop last year in Buenos Aires, and we have weekly meetings. So this is a large collaboration of people that is pushing to build in many aspects, right? Not only the simulations and the data analysis, also for the readout system, right? There are a lot of improvements also in that area. And as I tell you, most of the people involved in this Violeta effort are also part of the CONNIE collaboration. So at some point, these two efforts will merge in some way. So we are happy of that, because a lot of expertise coming from the neutrino analysis will merge with all the expertise from the skipper community that is pushing and trying to understand the background.
Guillermo, you have to wrap up, Guillermo, sorry.
Yes, I have just one more slide, and that's it. If you go to the next one, please. So there's a lot of things that you can do, right? So if you have a couple of 100 grams array of skipper CCD, you can see sevens in a month, more or less, right? You can then see what is the sensitivity for in terms of kilogram day that is on the plot on the left. But the important thing is that if you see 7, you can do a lot of things, right? And this is new, right? This is a new channel that has not been used in the past. It's how to use the 7 enhancement to see other things, or how we can use this enhancement to be more competitive looking at new physics than other experiments, right? And that's the point that I wanted to make with the neutrino magnetic moment search here, where in gray you see the current limits, right? The current top limit here, this is Xenon 10, this is what we heard last week, right? And they say that they have a small window there where they claim that they favor that particular region for the neutrino magnetic moment. And this is what Violeta can do, right? How an array of skipper CCDs can address that particular region, and of course keep, even if the magnetic moment is not there, can keep pushing for the limit, trying to understand what is the true statistic of the neutrino particle, right? And of course that you can do a lot of things with dark photon, which is all the plots on the right. I don't want to go in details into that. I just want to again emphasize the fact that if you see 7, you can use the enhancements of this particular cross-section to look other things and to take an advantage position compared to other technologies. And that's the skipper capability, essentially, right?
So we can discuss this more, Guillermo, we can discuss this more in the discussion section.
Okay, that's good. All right. The last slide is just a conclusion, just to give the idea that I would like to emphasize that we should push for this particular technology, the skipper CCD, that has been created from the very beginning in Latin America. And also in this particular case, we have the nuclear reactors that are the most intense neutrino sources, and we have a lot of them in Latin America, right? So we should push for the combination of the two things. That's the main point that I want to make here. Thanks a lot.
Thank you, Guillermo. Thank you. So people can ask questions to Guillermo in the Slack channel, and then we take this up in the discussion session. So next, is so Andes. I don't know.
Thank you, Rogerio. So I'm going to tell you about Andes, a plan for an underground laboratory located between Argentina and Chile. The idea came 10 years ago when we heard about this Agua Negra tunnel, which was planned between the province of San Juan in Argentina and Coquimbo in Chile. And the idea is that during the construction of the tunnel, you have a unique window of opportunity to build an underground laboratory, which would benefit from the infrastructure of the tunnel. And so the overhead of the costs for the tunnel is not, if you don't do it when the tunnel is built, then you lose the opportunity. So it's a very short window of opportunity. And we've been working on that in the last 10 years to try to make this a reality. So the nice thing about working in a tunnel when you have an underground laboratory is that you have a horizontal access, so you can access easily to the lab in comparison to working in a mine. And also since the beginning, we aimed at a big infrastructure, and so we also aimed at an international consortium and not only a laboratory, Argentinian one or between Argentina and Chile, ready to make it international. So next slide. I'm in the neutrino section. So even if Andes is much more than neutrino, neutrino is an important part of it. And so I'm showing two slides of the last Neutrino 2020 conference last week. So this is the list of underground facilities in the world where you can see Andes. So there are only two facilities planned in the Southern Hemisphere, Andes and Sopol in Australia. Sopol is about to be finished probably next year. They had some delays due to the COVID, like everybody, but probably next year it will be up and running. And we have Andes as a nice opportunity in our region. Next slide. So in the next slide, you see this on the right-hand side, the size of Andes compared to Sopol, which is a small dot just on top of it. So this is really, really the main selling point for Andes, that we are going to be big and we are going to be deep. If you look at this graph, the only lab which is bigger and deeper, which is the biggest and the deepest lab in the world, which is a Chinese one, Jinping. So there is no way anybody can compete with Jinping. But if you look at all the other labs, they are either not as deep or not as big as what we planned for Andes. So this really makes Andes a lab which can have a worldwide impact, not only for us, but really for the international community. And I've also highlighted two of the points that Yaret made in his slide. The fact that many facilities are crowded, so there is a lot of interest for something like Andes, and also that a lot of the big ones are focused on one experiment, just like DUNE in SURF or Hyper-K in Kamioka, while Andes will be multi-propository. And the second point is the strategic planning, which is active everywhere. And so that's exactly what we are doing in Latin America. So I think that's also a good point to see that we are doing the right things as of today. Next slide. So I have this slide on all the things that you can do in Andes. So there's a lot of dark matter. In particular, well, there is of course this long-standing signal of Gamma Libra, which would need an experiment in the Southern Hemisphere. Probably it will be killed or observed by someone else before Andes. But for Andes, it's something very interesting to go for the fourth generation of directed search experiment, and also directional one. For example, there is here's the logo of Cygnus, which is a directional experiment consortium, which is planned to have sites, a lot of different detectors in different laboratories. And so they are very interesting in coming to Andes. Then Skipper CCD, I'm not going to talk about them. You've already heard a lot about them in this session and previous sessions, but we are also wanting to, well, we are actually right now, as we speak, making measurements with Skipper CCDs to the dark matter in other places. And this we will want to move to Andes. So neutrinos, the topic of this session, geoneutrinos, and this is a very nice place for that. We also want to have the flagship experiment in Andes to be a low energy neutrino observatory. I think neutrinoless double beta decay is something very important in the field, maybe not developed that much in Latin America, but there is at least one group in Colombia I know of, which is working on it, and I know quite a few theorists working on it. So that's also something very important in underground physics and neutrino physics. And then there is a lot of other things you can do in underground laboratory. You have a clean lab for low radiation measurement. We will have a dedicated biology lab, and there is a big portion of the laboratory in itself, which is not for our high energy physics, but for geoscience, which is also, I mean, it's a multi-purpose laboratory. Next slide. So we have a current layout. So this is a design we have as of today, which was finalized last year in May 2019. We got the detailed engineering design from Lombardi, the company which designed the tunnel. It was $500,000, which was paid by the Argentine province of San Juan. And so, well, there is the details for those who are interested in seeing what it will be. Next slide. So this is my last slide, but I think it's the most important one, which is the politics about the lab, right? So I don't want to convince any of you to come and work in Andes now, because, well, we don't have Andes. We hope to have it very soon, but I think it's really what we are building all this community in Latin America for. So everybody working in a neutrino experiment as of today is building the manpower necessary to be able to build a big experiment in Andes in 10 years. So we should really see Andes as probably not for the next 5 years, but for the, well, it will open in 10 years if everything goes well. So it's really a long-term plan for us. So we have a lot of support here. I've listed, we have more than 70 signed documents supporting Andes. I've just listed the binational Agua Negra tunnel entity, which is a political and technical entity in charge of the tunnel. So it was very important to have them on board. And so they gave us the green light to add Andes and as an option for the construction of the Agua Negra tunnel. And actually, as of today, Andes is even a good plus argument they use in favor of the tunnel. So we are really well considered by everybody there. Then in Argentina, all the scientific institutions are supporting us. So the CONNIE, CONNIE, the Atomic Commission of Energy, the local San Juan government, and the Ministry of Science and Technology. The same thing in Chile, not science and technology yet because it's a new ministry, but we had the International Relationship Ministry, which was the one which was pushing Andes in the past. Then a lot of support, international support, including 2 Nobel laureates. There is a list on our website, and the list is separated in 2 parts, one which is international and one which is local, regional, which has a list of all the Latin American support we have, and it's about almost half of it. So we really have a strong support in the region for Andes, which is very important for us, right? We want it to allow us to use all the expertise we have been built doing the Geology Observatory, working in Atlas, working in other astroparticle experiments in HECAP, now working in DUNE. I mean, all these expertise we are building in experiments, sometimes abroad from the region, we can throw it into Andes in the future. So the official existence of Andes is as a CLAF unit, so unit into the Latin American Center for Physics since 2014. This legal existence allowed us to funnel money from Argentina and from Chile when we had to do the conceptual study and then the engineering studies for Andes, and it worked very well. And it is a base for the future Andes consortium. And then in each of our countries, we have different ways of organizing ourselves. And in the future, we foresee the structure, something similar to Sesame. I don't know if you know that. It's like a small CERN. It's actually a spin out from CERN. It's a synchrotron facility in the Middle East. And so it's kind of CERN, but small, and this is probably the structure we want to adapt for Andes, where Latin American countries will be most of it, but we don't want to limit that only to Latin America, and we also want to have other international partners in Andes, either directly as members or as observers. We've discussed, for example, with Germany and France as members, and we've discussed with Italy and Canada as possible observers. So this is the structure we expect for the laboratory. And well, we really believe, of course, that Andes it could be the perfect flagship for Latin America high energy physics research infrastructures. And I have to say now the last point, which is the negative point, which is even if we have the very green light for Andes from everybody in both in the science community, but also in the politics community, both in Argentina and in Chile. It's not the same for the Agua Negra tunnel itself. And we cannot build Andes if there is no tunnel. We've looked at other sites for possible sites for Andes, but none of them would have the depth of the Agua Negra tunnel. And in that, and if we wanted to build something like Andes somewhere else, then it wouldn't make sense to make such a big lab. And so it would really totally change the scope of Andes. So we are really needing this Agua Negra tunnel. And the situation in the last 3 years has been kind of frozen from a political point of view, both by the Argentine and the Chilean government. But we had a change in government in Argentina last year in December. And we can hopefully believe things are going to change. Up to now in Argentina, we are renegotiating our debt. So the last renegotiation was proposed yesterday. So we will see probably within a week if it's accepted or not. And so if this is accepted, then the government will look again at trying to build big things like the Agua Negra tunnel. And then we also had the coronavirus as everybody. So the situation is a bit flaky as of today for the tunnel. But we hope that within 2 or 3 months, the situation would be more clear for the tunnel. And what is clear for us is that if the Agua Negra tunnel gets a green light, then there is, I would say, 80 to 90% chance that we would get Andes into it. Thank you.
Thank you, Xavier. I think Andes is really interesting and flagship project, as you said. So we should talk about more. We should talk more about Andes in the discussions. Thank you very much. Last but not least, I think we have Segreto talking about the Brazilian Community Report on Neutrino Program at Fermilab. So thank you, Ettore. Are you? Go ahead.
Can you hear me?
Yes.
Okay. First of all, let me thank the organization for the invitation on this important and relevant initiative in Latin America. I will make a brief summary since many things have been already exposed by Juvis very well about the status of the Latin American, not only Brazilian, effort in the DUNE experiment. Next slide, please. As you have heard, DUNE is a very large collaboration. Up to now, we have more than 1,100 collaborators from, we are approaching the 200 institutions and more than 30 countries plus CERN. So it's a worldwide experiment. Next slide, please. And in this, there is a significant and collaboration of Latin American institutions. Here in the same style of the DUNE worldwide plot, we show what are the Latin American countries which are involved. So there are institutions, many institutions from Brazil, as you have heard. There are institutions from Colombia, from Peru, Paraguay, and from Mexico. Next slide, please. Just a few words, since Lewis already highlighted the main feature of the DUNE experiment. it is clearly a complex experiment with many components we need to fit together. First of all, the very intense neutrino beams, which will originate from Fermilab in Chicago, will start with 1.2 megawatt and then will be eventually upgraded to 2.4 megawatt of power. Near the detector, just close to the production of the neutrino beam, and a huge far detector in the surf laboratory with the final mass, which will total about 40 kilotons of liquid argon. And it will be constructed with a staged strategy in pieces of 10 kiloton detectors. The first two detectors will be of the single phase technology, as highlighted by Dewis, and in which we are substantially giving our contribution for now. There is a mistake, is that the first model installation is not starting in 2021, it's 2024, but the construction, for example, for our subsystem, the photon detection system, will start at the end of 2022. Next slide. DUNE has an ambitious science program, as all of you know, and we'll try to answer or give contributions to some of the fundamental questions which are still open in industrial particle physics scenario. First of all, in neutrino selection physics, trying to give contribution to clarify the question of CP violation in the electronic sector, mass hierarchy on neutrinos, and make precise oscillation measurement in the three-flavor paradigm. We plan to contribute to the nucleon decay search, which is predicted by many beyond standard model theories, but not yet observed. And as all of you know, you need a very large mass to have some kind of sensitivity to this kind of decays. And it will act as a supernova observatory, which will be able to collect neutrino for galactic or near galactic supernova collapses. Next slide, please. There is a very active community in phenomenological studies in Brazil and in other Latin America countries, particularly for what concerns beyond standard model studies. Brazilian groups are participating constantly to the activities of the working group on this item of the DUNE collaboration, in particular for an analysis on large extra dimensions, no standard neutrino interaction. There are also very significant contribution to the short baseline program, again at Fermilab, on sterile neutrinos, in particular on the analysis of heavy neutrino decay. Next slide, please. The main contribution on the hardware side of the Latin America institution to the DUNE far detector is the construction, is development and construction of the photon detection system, which is based on technology developed in Brazil at Unicamp, DIC Sarapuca, and which is the baseline choice for the DUNE single phase far detector. Our approach in this case was to propose an ambitious program that is proposing to a new system for the liquid argon scintillation light detection, competing with the system which had been proposed by other institutions. This idea growth, we aggregated several Latin American institutions, and in the end, we were able to attract a lot of European and American institutions from the US mainly. The result is what you read here. The consortium currently includes about 46 institutions from all over the world, which are at the moment equally distributed between among Latin America, Europe, and North America. And more than 250 collaborators. This means that it's a significant fraction of the collaboration, which is collaborating in this effort. And clearly, it also opens opportunities for Latin America collaborators, opens the horizon of the possibilities. So the optical components will be mainly been developed and will be built in Brazil, because this is the final goal, to build what we developed here in Latin America. So the optical component, the optical filters, the wavelength shifters, and so on will be the mechanical structure will be built in Brazil, and the radar system based on a definite concept has been developed by collaboration of Colombian, Peruvian, Paraguayan institution together with Fermilab. The goal is in this case to build this system in Latin America. Next slide, please. This is where the story started, the ambitious program that I talked about at the beginning. So we proposed to install some models of our system. You see here one piece of the anodic plane of the proto-DUNE prototype, the proto-DUNE detector, which is the DUNE prototype at CERN, together with other models. The models are this weightish bar inside this bigger wiring plane to demonstrate that our technology was competitive. This happened starting from 2017. Next slide, please. And we had excellent result, which demonstrated the validity of our proposal. And in fact, you can see we installed only 2 models since our proposal was very late, while there were about 30 models of 2 different technologies. So you see on the plot on the right, the highest peak is the peak of next slide. Okay. In the latest period, the Brazilian side of this effort got involved also in another sector, and in particular in the liquid argon purification system. And I think this is a very good initiative, and which was promoted, as I said, 1.5 years ago by FAPESP here in Brazil, but which can be easily extended to the rest of the Latin American collaborators. And in particular, we have a proposal. We are working already on this, of performing fluid dynamic calculation, simulation, and project conceptual design for the recirculation system of the liquid argon, the system which purifies the liquid argon to keep it at the detector grade. And this includes all these sub-items that are listed here. So testing the temperature monitoring system, test new purification method, media, synthesizing this material, and more ambitious things like the design of the liquid argon gas argon purification system, which has a lot of challenges, as you could have imagined from the previous talk on Andes. This is an underground experiment, so everything needs to be built underground. In the case of SURF, it is a mine, so all the components need to go down with an elevator. And then the production and construction of purity monitors and contribution to slow control development. Next slide.
Today, Are you wrapping up now?
Yes, I'm finished.
Okay.
So this is really an excellent opportunity for Brazilian companies and hopefully for other Latin American companies too. Next slide. As I said, we are also contributing to the SBN program, which has been used mainly as an R&D support for the development of the photon detection system of the DUNE. Next slide. And in fact, a significant number of about 200 Arapuca, X-Arapuca will be installed in SBMD. And they are being produced and constructed at Unicamp. Everything is delayed because of the COVID emergency. But as soon as the activity will start, the production will end up. And the 200 Arapuca will complete the photon detection system of the SBMD, will contribute to the R&D for the X-Arapuca for the DUNE. Next slide, I think was, yes, these are contributing also with software development, Monte Carlo simulation, studies on the dependence of the collection efficiency of the X-Arapuca from the photosensors, positioning and optical properties, Monte Carlo codes for SBND. We are contributing to the more general development of the collaboration tools. I think next slide, I think what is my last. So this is just an acknowledgement, just to show the support we are getting from our funding agency, because as we know, this matters, and hopefully it will go in the next years. Thank you.
Thank you. Thank you, Ettore. So I'd like to thank Harold and all the 8 speakers of the session. It was very fruitful, and I think it conveyed the very rich and impressive landscape that we have in Latin America for neutrino physics, exploring different experiments, different strategies, and the experiments are in different stages. So now is the time, I think it's the most important, where we open for discussions. So you can ask questions raising your hand in the chat. There's a way to raise your hand and look for hands that are raised. You can also write on the chat. Sorry, you can write in the chat. You can also write in the Slack channel. So we have a Slack channel called Neutrinos. And I start reading a question from Ernesto Kemp in the channel to Pietro Chimenti. If the SPMT can improve vertex reconstruction exploring the smaller time spread of the signal. So Pietro.
Hello?
We can hear you, Pietro. Go ahead.
Yes. Yes, I mean, the small PMT and also the electronics associated with them have a very nice timing resolution. So I think that it is a possibility to improve the vertex reconstruction. However, this is not the main objective.
Okay, thank you, Pietro. So Ernesto has another question, if it's not the same. So Ernesto raised his hand, so go ahead, Ernesto.
Hello, no, it's not the same question. I wrote a previous question to André Romero in the Slack channel, but if I can do it here, okay.
So he answered in the Slack channel, right?
Yeah. I read it, or can I?
But you're not satisfied with the answer in the Slack channel?
No, I didn't see it. Sorry.
It's written there. So go there, and there's an answer of that you wrote there.
Oh, okay, I got it. Okay. I'm satisfied.
So, yeah. Right. So I have a question for Guillermo about the Skipper CCD. So if you want to use Skipper CCDs for, say, dark matter searches, you need a large area. So what are the prospects of getting large areas for Skipper CCDs?
The large area, you mean a large mass, right?
Yeah, a large mass, sorry, yes.
Yeah, no, that's fine. So the prospects are the following. there's an ongoing experiment, and thank you for this question because I was trying to raise my hand, so I will finish with a question, right? So there's an ongoing experiment that is called Sensei, looking for light dark matter, and that's happening in Minos. It has a few grams in Minos and a few grams in Snow Lab, and in the next couple of months there will be a deployment of the full-scale experiment, which is up to 100 grams running at Snow Lab, right? After that, there's another collaboration that is called DAMIC-M, right? That is also willing to use skippers to look for dark matter, and that's an effort in the US and in Europe, and that's the reach of that is to build a 1 kilogram experiment based on skipper CCDs, right? And that has a time frame of 5 years, something like that. And then after that, there's an experiment that is called Oscura, which is in at the very beginning stage. This is driven by the US, by Fermilab and other universities, that is willing to build a 10 kilogram skipper CCD array for dark matter searches. So my question, since I don't know if that answered your question, I would like to ask Xavier if he thinks that, for example, an experiment like Oscura could be an experiment that can be installed in Andes, for example, that if that enters in the timeline of the Andes laboratory.
I do think so. I mean, that's the reason why we here in Bariloche joined the CCD stuff almost 10 years ago, and so now we are part of DAMIC-M. So we are working on this 1 kilogram experiment in Modan. Each of the CCD is 5 grams. That's around 200 CCDs or 500 CCDs if you can make them 20 grams, which would be the target, so to complement the answer to Rogelio. But what for Andy, the thing is, what are we going to do in 10 years? And I'm not sure that in 10 years, if 10 years is the right time scale for Oscura, I would hope for it to be ready before that. So maybe the next step after Oscura could come to Andes. So especially for dark matter in Andes, it's very difficult to answer because it's a field which evolves a lot, which might make a 180-degree turn if we detect dark matter. I mean, if it's an axion, like I doubt, but xenon 1-ton signal has, and it's not tritium, or if it's, I mean, depending on what it is, probably we will focus a lot of effort there. And I think we will be ready at this stage. And if not, then of course, I mean, we will install whatever you are working on in 10 years.
Thank you.
Thank you, Xavier. Thank you, Guillermo. Marcela wants to ask a question. Go ahead, Marcela.
Yes, I just wanted to ask to Guillermo, can you say a bit more about Oscura? So exactly related to the question or to the answer of Xavier. What is the time frame and what is the status of, you are thinking, I suppose it will come more clear after the first upgrade in mass for a skipper, but can you say something more concrete about Oscura?
Yes, so this is an R&D funding that has been given by the DOE to Fermilab and other universities to do the R&D for a 10 kilogram experiment for light dark matter searches. The R&D, the idea of the R&D is that because every time that you increase in mass, you have to reduce your background essentially to be competitive, right? So you have to put a lot of attention on other things that you don't need for lighter experiment. So the R&D process is, or the funding is for 4 years, right? And that's the R&D process. And depending on the results of that R&D, there will be more funds for to build the experiment.
Is that okay, Marcela? You want to follow up on this?
No, that's fine. Thank you. Thank
okay.
you.
Maybe before going to Alinka, there's a question related to that Harold wants to ask. So Alinka, Harold, go ahead because it's related.
Okay, thank you. I didn't know how to raise my hand. Okay, I think that one of the most representative directions that we must to consider in this discussion is how much are we engaged in a direct dark matter experiment? Because as far as I know, most of the contributions have been theoretical, but we already know that there are a lot of large collaborations that can offer the programs, but we don't have such a thing like a proper experiment to be really proud of that and to move ahead and to push ahead authorities on funding. So taking into account that as most of we really want is just to try to make possible Andes, because from my point of view, and I think that as a collective reasoning, it is a good option for our community. Taking into account that probably that would be feasible, probably there will be a proper moment when we have to discuss what to locate right there. I would like to know first if Javier can tell me a little bit more about, there will be certain point where the discussions around what kind of experiments, regardless if physics or biology or earth science, should be located there, and how would be this kind of decisions about the size of the experiment that could be running over there, which is connect with the Guillermo reasoning, because I think that that the Sensei experiment and the technology behind the skipper CCDs are very good opportunities and concepts to be considered in our near future.
Yeah, so the structure we expect to have for Andes is kind of Sesame, so like kind of CERN. So each contributing country would have two representatives in a board, one from, let's say, the agency and one from the science. And then this board would discuss. The space we have is, we have a specific space, a specific lab for biology. We have a specific portion of the lab, which is a long tunnel with two small tunnels and then some places for geophysics, because the necessity for geophysics are quite different from geoscience, are quite different from ours. And then there are a few big places, which are where we are going to put our big experiments. So for these big places, it would be this consortium which would discuss based mostly on the physics, right? And I think we will also work a lot with other laboratories. So even if usually in physics we are used to competition among experiments, in the underground physics community, there is a lot of collaboration between underground laboratories on how to plan the future, and where do we want to put different experiments. So this will be a discussion among this governing entity of Andes in collaboration with other underground laboratory directors to see what we install in the lab. And just to get an idea, so we have a space for neutrino, which is 30-meter diameter, 30-meter deep pit. And then the big cave is 23-meter tall, 21-meter width, and 50-meter long, which is half a Grand Sasso cave, a little bit higher. So it's really a big space. So it's I don't think we will have issues in having experiments, and probably if you want to host bigger experiments than that or more than that, then the cost of the experiment starts to be so large that it just makes sense building the tunnel and the experiment at the same time. So we had a review by Tony Noble and other lab directors of the design of the lab with respect of its size, to make sure that we were on spot, and they were very happy with our ideas.
Okay, Javier. So Alinka has a question. Go ahead, Alinka.
My question is, if the
You just muted yourself.
okay, No, my question is to Xavier Bertou, and it is about the possibility at Andes to install a small accelerator to measure nuclear reactions of very low background, to be able to measure very low cross sections of nuclear reactions of astrophysical interest, as it is in Luna at Gran Sasso.
Yes.
Yes, I mean, Claudio has a mic up. I don't know if you want to answer, but
No, go ahead.
Okay, we have a place for that. So one of the extra caves we have is a long a cave. It's separated from the rest of the lab, since we don't want to get background when we go underground. So we have a place which is foreseen for a few MeV tandem accelerator to make this kind of low energy cross-section measurements. So it's a possibility. Then of course, I mean, we have the place to do it, but then someone has to do it, right? So someone in the community has to take that and bring the experiment to reality.
This is because at my university, at my laboratory, there is a group of people who are working at Luna sometimes, and they are capable and very interested. So this should be something that we could begin to discuss about.
Well, make them contact me. I will be very happy to show them what we have planned and discuss that with them. Thank you.
Okay, thank you very much.
Okay. Thank you, Xavier. Thank you, Olinka. I don't see any hands, so I ask a question. If I don't see any hands, I ask a question, okay? It's a question for the liquid argon people. So listening to the talks, it seems that there is a knowledge here in the area in Latin America of liquid argon detectors, especially detecting light from the liquid argon. So the question is if that could be used also for, again, dark matter detection, because there are liquid argon detectors for dark matter detected. So maybe Epori can comment on.
Yeah, I can comment on this. Clearly, the liquid argon technology is the other phase of liquid argon technology is dark matter. Dark side is the leading experiment in dark matter search, and there are groups collaborating in dark side. I mean, dark side, Anamelia, Ivone, Maximo at USP. What I see right now as an interesting opportunity, something which is being developed right now, is the xenon doped liquid argon option. This is just being tested at CERN for DUNE as an opportunity, and eventually it could be very interesting also for dark matter experiment. It will make also attractive probably our technology, the Arapuca technology, for this kind of experiment. So I see some kind of possible path toward new detectors. Clearly we need to think to several tons of mass of detectors. So this is the scale we need to think about. But clearly there is the possibility. It's something which could be investigated. It needs to be investigated probably.
Thank you, Ettore. I see that Marcela has her hand.
I have a question for Ettore. So, what is exactly what is being done with xenon dope at you say at CERN? So how is it related to to dark side? Sorry, to dark side. And I understand that Arapuca will be interesting from the point of view of the readout, but can you say a bit more about what DarkSide is thinking about that, or is that part of DarkSide collaboration, or can you expand, please?
I don't know if DarkSide is investigating this. I mean, it could be interesting for future dark matter experiments for sure. What has been done at CERN, the ProtoDune, the single phase at the end of the runs, which is ending right now, is to dope the liquid argon with the small amount of xenon at the level of 20-30 ppm. And it was observed that almost all the light was shifted from the 128 light of liquid argon, which is very uncomfortable, to the xenon wavelength. That is 174 nanometer. This is technologically very interesting because quartz is transparent to this wavelength. So you can think to avoid having wavelength shifters, organic wavelength shifter, as is now the case for the liquid argon dark matter experiments, and could help in making more sensitive detector with the sensor specifically detecting direct xenon shifted light. It opens a series of new technological opportunities, let's say. Dark side, I don't think is going in this direction for the next detector, the 20-ton detector. I don't know, probably in the future they will think about, but it's something which is attracting the attention of people.
Sorry, Ettore, and for DUNE, that means that you are thinking about that for the other two detectors, not for the first two, or is more?
Yeah, no, I'm thinking it too for the first one too.
Oh, okay.
This is something which is being discussed. There is the involvement of CERN, which is very interesting in this development. The test proton was very successful in the sense that what we found that we need a really small amount of xenon to do the work. This translates in a series of benefits and with very minimal cost. And so we are evaluating the possibility of doing the same thing also in the first far detector. So it's doping liquid argon with xenon.
Okay, thank you.
You're welcome.
Thank you, Ettore. Thank you, Marcela. I think Harold has another comment that he put in the Slack. Maybe you can just read out.
Really, a comment just trying to give us some feedback on the discussion about what kind of techniques and arrays should be really be considered in order to enhance the discovery potential in our region regarding, I don't know, in that case was discussing about galactic sources or neutrinos. So that's not more than a comment than a question. So just trying to give some inputs. I think that is very important in that sense. And let me to comment a little bit more, just to consider seriously what could be done from a combined analysis point of view, because obviously capabilities on the northern hemisphere, where most of the well-recognized observatories are located, differs a lot of the reality we have right here. So what is regarding to the high energy regime in neutrino physics is up to the large arrays we can just develop. Okay, so I think that is try to really define a policy and a balance to consider all these frame into the global neutrino picture, not only for neutrino properties, but analysis of sources of the extragalactic origin or beyond that.
Okay, thank you, Harold. Yeah, we should talk about this also because Auger has some sensitivity to very high energy neutrinos. So hopefully, when we have an Auger talk, we should discuss this. Marta has a question.
Okay.
Sorry, Harold. Go ahead.
No, I'm sorry. That's only the last comment in that direction, because yes, what we want to really to take care about what is the channel we are trying to look at, because most of the neutrino telescopes just point for the mu neutrino component, but if we want to really explore more in the dense regions to really comprehend what is the acceleration mechanism, we look at the other components at the tau neutrino, which is the proposal that is very innovative in that sense.
Yeah. Marta has a question.
Yeah, I had a question for Andres Romero about who are the Latin American, or which are the Latin American institutions participating in that project, and what is the cost of that project?
So the Latin American partners are mostly in Peru at this point. It's Universidad Católica in Lima and Universidad San Agustín in Arequipa. The cost is still something we're trying to figure out. I mean, we mentioned it in the white paper by analogy with Auger. We think it's somewhere between Auger and Ice Cube costs. But of course, that depends on a lot of details, right? So once we've solidified our analysis, the next step is to study the feasibility of constructing in the canyon, which at this point is unknown.
So a follow up on that, I mean, do you have a strategy for garnering more support, or participation from Latin American institutions? Who's kind of driving this?
Yes, well, I'm the PI. I think once we have the initial analysis out, that'll be the time to start growing the collaboration and understanding what are the different contributions that are needed to build this. But yes, we are open to making this a wide international collaboration once we have everything, all the information we need to know how to get started.
Thank you, Andres. Thank you, Marta. I don't see any hands up. So I ask a question. I just want to ask a question to Guillermo, just to show my ignorance. Is it anyways possible to build these skipper CCDs in Latin America, or the technology is just beyond our reach?
No, it is not. I mean, let me say more about that. So first I want to make a clear point that El Centro Atómico Bariloche is already participating in the design of the new skip, and essentially, conceptually, this is to move the current fabrication, I mean, the design from current fabrication processes that use some semiconductor technology that is kind of old, right, to replace the design for the new CMOS fabrication processes, right? And if you build a skipper with CMOS processes, this means that you can fabricate it everywhere, right? Using all the standard foundries that are around the world. And I think that, I don't know the details. I know that Brazil has or at least had a foundry, a CMOS foundry. I don't know how it works. I don't know if those are digital or analog processes, right? I'm just trying to give an example. So the answer is yes. I mean, there's already an ongoing effort to do design, skipper design, and more standard fabrication processes. And after that is achieved, then that's it, right? You can use more standard, cheaper foundries to build the sensors, right? The key of the skipper sensor is, I didn't go into the details, but the key is the floating gate, which is essentially a way to measure the charge that has been created, right? And that particular structure that is called floating gate can be built on any semiconductor process. So there's no limitation on building this skipper sensor on any semiconductor process, essentially. So I think it is very promising, right? And there's a group that is already working on that. Yeah.
Thank you, Guillermo. So yes, we have a foundry here in Brazil, which is for very low-tech ships that are supposed just to pack cattle or something like that. I just read on the news today that the government wants to close this. So
okay.
That's how.
Okay.
But maybe this is a reason why they shouldn't close it, right? Okay. So Xavier has a question. Yeah, Xavier.
Yeah, to Andres on on the neutrino tau. Did you look at how the limit compares to what Grand wants to do? You know, Grand is a radio array. It will be discussed on Friday in the Astro session.
I think we're at a different energy band, right? Grand is sort of 100 PeV turn on, and this is targeting the PeV energies where we know there is a flux.
And for PeV, you cannot do that with radio because
yeah, we of course I'm a radio detection person, and the first thing we did was figure out that you needed a 30-meter radio dish to be sensitive to these energies. So so that's how we arrived at the particle counter approach.
Okay, thank you.
So thank you, Xavier. Thank you, Andres. I don't see any hands, and I ran out of questions. I don't see any new questions also in the Slack channel. So and people here in Brazil are getting hungry because it's time. So I propose to close the session, thanking again the conveners, of course, Harold and the others, and all the speakers of the short talk. I think was very productive. And you can continue discussing things in the Slack channel. And I will leave the Zoom open if you guys want to talk or anything. And so we should resume at 3:30 São Paulo time for the session on the national roadmap. So thank you very much for